Okay, I believe we're streaming now. So we want to talk, excuse me, we want to talk about some problems out of chapter 13, which we're going to start on page 120 in the workbook. And I'll start with the screen share. If you came to the earlier section and you stayed the whole time, it's basically going to be a rehash of that. And so you're welcome to sit around here and just leave your screen on and mute. And then if I say anything interesting, then you could listen in then. So those of you that did come earlier, I can't remember who all stuck around. All right, so let's take a look here. Oops, wrong one. I could tell I have a sneeze coming. Sorry about that. All right, and escape from the planet of the physicists. So this is a fun little problem. It's actually somewhat standard, just not the way I wrote it up. But the basic idea is, imagine you're sitting here on the surface of the planet and you want to escape that planet. Obviously, you're going to launch with some initial speed v. And as you go upwards, you'd expect your velocity should slow down. And the idea is, if your velocity is approximately equal to 0 when your height or your altitude above the surface of the planet is very, very large, we'd say you've escaped. Now think about this. If you launch it pretty slowly, we expect you might come up and then come back down. If you go a little bit faster, you might make it a little bit farther before you come back down. The idea here is you basically keep moving at a very, very, very low velocity away from the planet. All right. And so that's what I mean by escape the planet. So if you think about it, just showing you with motion, right? If you go too slowly, you don't escape. But if you go fast enough, as you get away, you slow down, but you're still creeping off screen like that. And so the idea is that's what it means to escape. So let's get in there. We've got the planet's mass, planet's radius here. The people squeeze into the space pod and they launch off the surface at speed v. We're going to assume drag is negligible, so we don't have to worry about air resistance. Obviously, you'd have to account for that in a real life situation, but for now, we're going to ignore that. All right, so if that's the case, what type of problem might we do to figure out the required initial launch speed? What type of problem does this look like? Are we going to do kinematics, forces? What do you think?
Kinematics or energy?
Well, if you do kinematics, what's an equation you might write down? That relates v and v final and some distance.
V final x equals v initial x plus the acceleration t, or axt.
Okay. Now I'm going to write that down and I want to talk about it. The other one that you might use could be v final x squared equals v initial x squared. That's kind of our gut reaction. When you see a problem and you maybe want to figure this out, we might want to grab this equation. However, why are these a bad idea for this problem? Why would we not? Say again?
The change in acceleration?
Yes. So the problem is, as you move away, the force changes. So here there's a large force. Then out here, there's a small force. And out here, there's almost no force. And so we see that if the force is changing, I hope you agree that the acceleration given by force over the mass of the particle is also changing. This equation is true at any one instant, but it keeps changing. So as a result, it gets very difficult to use these kinematics equations. It could be done if you coded it, and we'll do that in lab, but it turns out kinematics is a bad idea for that reason, even though it's kind of the obvious thing we jump to. So that was a good thought. So kinematics is going to be problematic. Other ideas?
Now energy then.
Yeah, exactly. So if we write down the energy, let me just make this a little bit bigger here. All right. So in this case, what types of energy let's write down the energy equation. I hope you agree that E initial plus work done, non-conservative and external should equal E final, right? That's kind of our energy equation. All right. What types of energy do you think we have? What's one type of energy we have in
MGH.
this scenario? But we don't. So what's the name for that type of energy?
Is that the gravitational force?
Exactly. Now we don't use MGH anymore. So I'm just going to say we have U subscript G.
Okay.
Because that's the one we have a new formula for. Do you remember the new formula for it?
Not by heart, but it's on like page, the first part of the chapter.
Negative G M big M over R squared.
Over R. The force has the R squared. The energy has this R in it. So later today, I'm going to show you how this relates to MGH, but not right now. Okay. So that's we have. Okay, cool. That's one type of energy. What's another type we have?
One half mv squared, so that's going to be I think it's K.
Yeah, kinetic.
Yep.
Nice. All right. Now, wait a minute. Don't we have to figure out the work done by gravity as well? Because there's a work equation here. Am I going to need to figure out the work done by gravity?
No, because you already have it.
Exactly. Already accounted for that. Gravity does, it's a conservative force. So gravity is not non-conservative. Gravity is conservative, so we've already accounted for it. What about the work done by air resistance? We're ignoring it. Woohoo! Negligible drag. There was a D somewhere over there. Negligible drag. So that's it. All right. So there we go. Two of these terms are equal to 0. Which two? What is one term that is equal to 0 in this equation?
Definitely K final, because the final velocity equals 0.
Yep. Because of this, that goes to 0. What's the other term that equals 0?
Would it be gravity at the planet? No.
Nope. So what's left?
And that either means the gravity on the right side or the kinetic energy at the beginning. I guess if you start from rest.
But if you
no,
start
he's trying
from
to find me.
rest,
Sorry, you're trying to find me. Oh, then it should be I guess the farther away you go then.
well, let's see. Does that make sense?
Yeah, it doesn't have a force anymore acting on it.
If we go really far away, if I say something divided by infinity, now that obviously we aren't going to infinity, and this is mathematically not rigorous. If you put something over a number that's close to infinity, that's a very large number, what do you get?
0.
Yeah.
0. So that's why these two terms on the right go to 0. So far, so good. Now let's take a look at the solutions. So here we go. Let's just take a look, see if, oh, come on. Take a follow through. What we were saying is this goes to 0. Otherwise, you don't escape. We're finding the minimum velocity to escape. And I'll go into that more in a second. And then we said, well, if this goes to infinity, that term also is going to go to 0. So both go to 0. And if we solve this remaining equation for V, we get that. So take a second to look through that. This is how we could use energy to calculate a speed in a gravitational problem. Very cool. This is called the escape velocity because it is the minimum V to escape. What would be different in this problem if we did this problem again, but we used a speed that was in this number? For example, pretend this number comes out to be 12 kilometers per second. Or actually, let's say it turns out to be 11.2 kilometers per second. Okay. And then I want to redo this problem with 12 kilometers per second. What would be different? If I used a speed larger than the minimum, how would that affect the work up above?
The final velocity would, you still have some kinetic energy.
Exactly. This would not be zero anymore. So that's the main difference here. If you're going to do an escape speed, the trick is set this term to zero. Then any larger speed, the final would not be zero, but you still escape. Is that making some sense? If you want escape speed, set the final to zero, and that gets you the minimum speed to escape. Any larger speed plugged in there, V final would not equal zero, but it would still escape. All right. Here's a fun one. Check this out. Well, let's just do this. Let me go back to the, let me make this smaller. Let me go back to here. Make this smaller. Okay. What if this planet is Earth? Here's the mass. Here's the radius, which is about 4,000 miles. The number for that, if we actually punch in the numbers based on Earth, we get that 11.2 kilometers per second right there. So that's not meters per second, it's kilometers per second. That's very, very fast. That's moving. Okay. So if you're curious, if you could throw a ball at 11.2 kilometers per second and air resistance was not present, you could throw it off the surface. It would be interesting to see what that number is for the moon. If you did the same calculation, you'd change the mass, change the radius, you know the numbers, you could calculate the escape speed for the moon. That you could figure out how likely it is to throw something off the surface of the moon. Or, you know, what, this is a legitimate problem. What if you were sending people to the moon? You'd be like, well, is it possible they might accidentally jump off the moon and escape into space? The moon has less mass. It's a smaller radius. Is it possible? Well, what you could do is run the numbers with the moon's mass and the moon's radius and find out what that is and find out if that's even realistic. Throwing objects with a catapult or something, maybe you could launch them off the moon. I don't know. I haven't run the numbers and I don't know. So you could actually do the math and see what speed you would have to throw something to cause it to fly off the moon's surface. All right. So anyways, that's the idea of how that might be useful. All right. Let's take a look one step further here. Maybe today, computer. All right. Let's say you're really excited to finish lab tomorrow and you get out your AK-47 and start shooting bullets straight up in the air, because that's what I usually do when I finish lab. Get out the old AK and go nuts. Why? Yeah. So what's going to happen here? If you go outside with an AK-47 shooting bullets up straight up into the air at 700 meters per second, they escape. Will they escape the planet Earth?
There's still air resistance.
Well, one, there's air resistance, but two, even if there was no air resistance, this is less than 11 kilometers. That's 0.7. This is 0.7 kilometers per second. Let's stick a leading zero on that for good measure. That's a lot less than 11.2 kilometers per second. This is a bad idea. If you shoot bullets into the air, they come back and could, in theory, kill people. So, sorry, don't celebrate lab by shooting your AK straight up in the air. All right. Sorry, I know that's going to really bum you guys out. But when you see people shooting bullets up in the air, you're just like, oh man, that could kill somebody when that comes down. The odds are low because what are the odds that it happens to randomly hit somebody? But it is possible. It could damage a building or something too. All
The
right.
velocity from the bullet falling down the same as it goes up?
What do you think? What's
I
your
would
gut?
assume it's way slower.
Yes. Why is it going to be slower in the real world when it comes? So it's going to launch here at 700. It's going to go up to some max height and the speed is going to be 0. So why doesn't it hit 700 on the way back down?
I've heard it before, and I think it's called terminal velocity. Something like it can't pass a certain amount of like speed.
And well, how about I just say it this way? Do you agree that it's going to hit drag? And so drag is slowing it down on the way up, but drag is also slowing it down on the way down. So yeah, and drag is what causes you to hit terminal velocity. So on the way back down, the muzzle velocity, it's not going to be like shooting somebody point blank in the head with an AK-47. Absolutely. However, terminal velocity for AK-47 bullets is probably still pretty fast because they're designed to be aerodynamic. So terminal velocity of the bullet, even if you hit that on the way back, you're in trouble. Yeah, this is crazy, right? If it goes up and down and there was no air resistance, that's equivalent to putting it right up to their temple and shooting them, right? It's that bad. However, with air resistance, it's a little less bad. So, but yeah. So if you're curious, look up terminal velocity of these bullets and see how fast they'll come back down. Still, I don't recommend it. I'm trying to cut back myself. All right. All right. Here's a weird one. Why is it often advantageous to launch satellites from launch sites close to the equator? Why is this here? What's the advantage in launching satellites from Florida, right? We launch them from Cape Canaveral, Florida, or Texas. We're not launching them from northern Maine or Alaska. Why?
Would it have to be due to how the Earth is rotating?
Something about the Earth's rotation. We need a certain amount of energy to get up there. If you're sitting at the North Pole, you're rotating once every 24 hours, but you're not traveling that fast. So your omega is at the equator, but not. So let me just do this. I don't know why I didn't think of this earlier. I had this sitting on my bed and I forgot to use it. All right, here we are, right? So imagine, okay, here's Florida versus, say, somewhere up in Canada. All right. When we spin this thing, if you look at the top, the points close to the pole or close to the axis do not move as rapidly as these points out here, right? So at this point, the points near the equator start with more kinetic energy. So if you start with more kinetic energy, you require less fuel to get the rest of your kinetic energy to escape or to get into orbit or to whatever. So the idea is we had a huge edge in the space race because we're sitting down here with Florida pretty close to the equator, right? And so obviously it's not full radius, but if you look at this from the side, it's almost the same radius as at the equator. So you're getting almost all of the Earth's rotational energy. And so you need less fuel versus, say, Russia, right? Yes, look at Russia. Very latitude north. So there we go. So yeah, the Russians probably would have beat us if they had Florida, right? They did Sputnik already, so they were clearly, yeah. All right. Anyways, enough on that. So now Lompoc is different. right? You could say it's in the southern United States. There's other considerations. Some of you probably know a lot more about this because you probably have relatives working at the base. But one thing you could think about is I've heard that Lompoc is great for polar launch satellites. So there are other concerns with launching satellites. One might be, what if the satellite blows up and falls back to Earth? It'd be nice not to kill everybody, perhaps. So, right, you could imagine shooting out over the ocean probably has some advantages. So there's probably something with that. And Texas, right, you could shoot over a body of water. There's a number of factors involved. That's not my expertise, but I encourage you to talk to someone who is and say, like, why is Lompoc good for polar orbits? And you could discuss that with them. All right, that's not my expertise. Cool though. So Vandenberg's probably not going anywhere time soon. Here's another one. What if you set the escape speed to c, the speed of light? Okay, well, if we look in here, what I'm saying is, what if you take this formula and set the velocity equal to c? If you do that, you could solve for the radius of a black hole. So if you plug in the Earth's mass with the speed of light, it's about 1 centimeter. So if all of the Earth's mass was compressed into a sphere of radius 1 centimeter, you got yourself a black hole. And this right here is absurd, right? This gives you an idea of how dense a black hole is. An entire Earth in 1 centimeter, like a marble, right? If you look at the diameter, that's less than an inch diameter. 2.54 would be an inch. This is insane. I can't fathom these numbers. It's impossible. But yeah, imagine putting the entire Earth into something the size of a ball bearing. You got yourself a black hole. Only when you have that much mass density can light not escape. Very, very crazy. It turns out this simple calculation actually gives you a correct estimate for the event horizon of a non-rotating black hole, sometimes called a Schwarzschild black hole. I am not going to go into great detail on that, but if you're curious, you could look up this stuff here and you could learn about it. Rotating black holes are called Kerr black holes. There's all kinds of different names, and yeah, so that's cool. All right, there's black holes. Whoops, let's get this. So there's just kind of a classic problem worked all the way through. It turns out we do this again in physics 163, but we use charges, and we call this, this relates to a thing called Rutherford scattering. So maybe you've heard of that in a chemistry course, but imagine you have like a charged nucleus here. Let's just keep it, let's say there's a proton here. Actually, let's say there's a whole bunch of them. So let's say there's like 78 protons here, and this is gold or something, right? So there's 78 plus signs in here. I just don't want to draw them all. All right, obviously there's some neutrons in there too. Got some neutrons. And the idea is, an old experiment was to take an alpha particle, which is essentially the nucleus of a helium atom. More on this in another class, but you could do a similar problem where you launch something directly towards here. And because in electricity, you have like charges repel, if you fire plus charges at plus charges, you could figure out how close it'll come, it reverses direction using an energy problem. So the point I'm trying to emphasize right now is this. Sometimes if the question asks about speed, and you know that the acceleration is not constant, consider an energy problem. Again, if forces are not constant, try an energy problem. Sometimes that will help you solve it. That is what you should get out of this. All right. It won't work all the time, but sometimes it's great. Let's pause for questions. Any questions? Okay, let's keep rolling. Here's another weird thing that we're going to talk about today. CubeSats. I don't know if you've ever heard of this or know what this is. CubeSats were invented, I believe, between Berkeley or Stanford and Cal Poly. So they were these two schools that got together and created these small satellites, literally 1 kilogram satellites, approximately. Some might weigh a little more, a little less. And it turns out, if you're into this, you can actually join a club at Cal Poly where you can be the people controlling the satellites and communicating with the satellites. And it's a club you can join and you could learn valuable skills. So if this is something that interests you, gravity problems and that, maybe keep this in mind if you transfer to Cal Poly, that club right away, and maybe they'll start by giving you boring, worthless tasks. But by the time you're a senior, maybe you could do something cool. So check it out, CubeSats. You can read the solution about it. Enough said. This particular problem, I went through it and did it for you. I think it's good because you could see about conservation of energy and conservation of angular momentum for an elliptical orbit. So you could go ahead and check that out if you want. Those of you, if you have old editions, double check the numbers on your book for 13.10, okay? Just look and make sure. I think I forgot to write in the mass, but I was assuming you use these numbers because this is a CubeSat of 1 kilogram, somewhat realistic, orbiting the planet Earth in an elliptic. All right. All right. Next. Ooh. Okay. 13.11. I'm going to start doing 13.11 here on the board. I'll let you look at it while I get it written up here. I'm going to get the other side cleaned off too, just in case we need both. All right. Almost there. Okay. Now, to be honest, everybody, listen up. This is not on the test, but I do think it helps to see where this came from. I'm doing this for a reason. I think you should just kind of watch and follow it, and that's about it. So we're going to go quickly through this, stress out about it. Let's just watch and have a good time and learn where the formulas come from. Now, I think there's some small amount of learning you get out of this, and we'll just take it as it is. By definition, potential energy. Now, this first step, we will do again in other classes, so it is worthwhile to listen. Delta U, by definition, is minus the work done by a force. Well, the work done by a force is the integral of that force dot ds. That's the definition. Now, I want to be clear. Let me just emphasize this minus sign here. Let me make this so I don't forget it. In this case, we're going to go from this position to that position. So in this case, I'm going from my initial value of R to my final value of R. Okay, so basically I'm traveling this way. What's a good name for that direction?
Positive I hat.
You could say positive I hat, but I don't want to. Positive I hat would be to the right. It's another way to describe it. In
What about to
spherical.
the J hat? Since
Well,
Oh.
that would be up.
Ri minus Rf.
I want to talk about radial direction. So I would call that R hat. I'm going outwards radially. And so I hat would have been correct, but it gets confused. So what I want to do is I want to say this is the R hat direction. And if I do that, ds is going to become a small amount of radius in the R hat. Now, some of you might say, why don't I just do X in the I hat? Well, because I know the force has radius in it, right? That's why we're doing it this way. It's just bookkeeping. All right. So now let's work this out. I'm going to remember this minus sign. I'm going to remember this minus sign. Okay, I remembered that minus sign. That's the one I always forget. I'm going to write R initial. I'm going to write R final. And now the force. What's the force here? It's due to gravity. Negative G. Wait, I should be careful. It's G M M over the radius squared in the negative R hat. And now I need to dot that with dr in the R hat. Well, we could do this one in a lot of different ways, but let me pause. Is everybody okay? That's just the gravitational force equation from whatever page it was. So now take a look. I got a minus sign and a minus sign. I could do that. I have an R hat dot R hat. What is R hat dot R hat?
Cancels out.
It's a number. What is R hat dot R hat? You're right that it kind of drops out, but why? What is the number?
1.
1. Any hat vector has length 1. And if you dot it with itself, it's always parallel to itself. So a dot Chewbacca hat is 1. Taco Bell hat dot Taco Bell hat is 1. I hat dot I hat is 1. R hat dot R hat is 1. Okay. So now at this point, I'm just going to rewrite. We got delta U is equal to G M M. Those are constants. The R hat, I think we're left with dr over R squared, going from initial to final. Notice when you do this integral, what do you get? Maybe if I write it like this, R to the negative 2 dr. You remember power rule? Yeah, there's a 1. You're right. Oh, maybe that was a 1 second signal. My bad. I'll give you a hint. It's that. You get a negative from the exponent because it's raised to a negative power. Raise the power, that's R to the negative 1. So it's negative 1 over R. Got it? The fact is, this is the equation we've been using all along. That's how we get it. There's where the minus sign comes from. Notice there were 3 minus signs that happened along the way. And if you read a book, you can get really tired and not see it. But I just wanted you to know the equation we are using comes from definition of potential energy. Definition of potential energy is delta U equals this shit. Well, this is the answer for delta U, but then I could just say, oh, well, U initial would just be this number, U final, and so it works out. All right, so that's how we get that. Now, any questions about that before we go on? Not too crazy. Just wanted you to know where that came from. Nothing else. Okay. Now, I have a trickier question here. Give me a second. Let me draw it up. let's say this is the Earth. Okay. And the center of the Earth is way down there. And let's say I take a box. And obviously this is a little bit skewed, but let's say this is 10 kilometers up in the air. Do you think I could use mgh? Or should I use u equals negative gmm over the radius? Which of these, whoops, sorry. These are two different equations that we have used for potential energy. This is what we started in chapter 8. Now I'm saying, no, it's this one. Which one do you think applies here?
I would use the right one because we don't know the radius. Is that correct? Or do actually?
You could look this up. It turns out the radius of the Earth is about 4,000 miles. Or it's whatever, I think it was 6370 kilometers or something. It was in some problem. I forget, just like a problem ago. I don't have it written down in front of me. My version's outdated, but yeah, something like that, right? So we do know the radius. Based off that, which one do you think you should use?
Now I'm thinking use the other one since we know the radius.
The short answer is you should be able to use either one. And at first, you're like, dude, you're telling me if I plug in the numbers for this equation and that equation, I'm going to get the same answer? Yes. And it looks wildly messed up. Do you agree? It looks like there's no way. This has got a negative sign. It's 1 over r. What? I don't believe you, Jorstad. Well, I was going to show you the answer as to how you could use either one. The key is, as long as this distance is small compared to that distance, which this is tiny compared to that, 10 is much smaller than 6,000, this should work. So let me show you how. The problem, if you want to have it in front of you, is 13.12. So let me get that fired up and show it to you while I erase the board. We're looking at this one. Okay. I'm going to be honest with you before we start this problem. If you are a physics major, this will come up again. Everybody else, maybe not. However, electrical, mechanical engineers, a number of different engineers may see this process used. So I'm going to explain why. So I feel a moral obligation to do it. I don't spend a lot of time doing physics only topics. This is one of them I feel I have to do because any physicists in the class need to see this. So everybody else, you could just come along for the ride and learn a math trick. That said, we use this trick again in physics 163. So it's not like it's a one-time deal. You're going to see it again in my class in the fall. So you may as well pay attention and just kind of hear me out here. All right. So let's do this. I'm going to start here with the planet. Very similar. R initial. I'm exaggerating right now. Whoops. So we've got R initial and R final. Now we could describe these as height initial and height final if I go to the surface of the planet. So we've got two different heights here, height initial and height final. Now, this is not drawn to scale. I'm going to assume that height initial is much, much less than the radius of the planet. Figure not to scale. I have to draw it this way so we could see it. Not to scale. We're also going to assume height final is much, much less than the radius. Okay, this is a really cool math trick. Let's see how it works out. Okay. Delta U is equal to negative G M m over radius of the planet plus height final minus negative g m m over of the planet plus height initial. That would be delta U. Now, obviously, I have minus a negative number. Nobody writes it like that. We write plus. This is the change in energy. This is going to seem a little bit weird, but I'm going to factor out everything I can, including R. Now, when I do this, I want it to look like that because this has the correct units. In order to do this, we've got to look carefully. I'm going to put a 1 over R times 1, whoops. Give me a. All right, so check out what I did here. Multiply this through and make sure you feel confident. GMM over R with the negative sign. If I multiply that in here, notice I have this little 1 over R. This 1 over R term will cancel that. My minus sign's right there. And now this one has the opposite sign. So it should be now become a minus 1 over R times 1 over, and it seems silly to do this, but just trust me. I know what I'm talking about. That's all I can say at this moment. It looks dumb. Eventually, by doing this, we can turn that ugly equation up here into mg delta H. That's what we're going to find out. Is everybody okay with this line? Hope so. All right. Now I'm going to clean it up a little bit. Negative G M M over R. And inside of here, I'm going to multiply this through. So this becomes 1 over 1 plus height final over radius minus 1 over 1 minus plus height initial over radius. Excuse me. Again, what I've done is I just multiplied this 1 over R through. 1 over R times R is 1. 1 over R times height final is height final over R. Similar right there. So far, so good. Now, in this case, look at this right up here. Well, we've got it. H initial is much, much less than R. H final is also much, much less than R. I hope you agree. That means this number right here is much, much less than 1. Again, divide both sides of this equation by R, and you get H initial over radius is much, much less than 1. Similar for H final. So I'm going to rewrite this another way. I'm telling you, this process is used all the time in a physics class. So any physics majors, you've got to be good at this. Watch this. This is 1 over 1 plus, I'll call this delta final. Here, delta is just a symbol that means a number much, much less than 1. So any of these deltas, that just means it's a small number. This is the standard way you'll see it written. Now let's go one step further. Give me a sec. Got to sit down. I'm so low on the board here. This is crazy now. This is equal to negative G M M over R times the following. 1 plus delta final to the negative 1 minus 1 plus delta initial to the negative 1. This seems crazy, doesn't it? It shows up in chemistry classes too. If you're talking about dipole moments and the forces, intermolecular forces, there's a bunch of weird spots this shows up at random times. Okay. So far, so good. Any questions to hear? What we have done is we have rewritten this first equation right here like this right here, where delta is a small number. We still have not changed anything. This is still exactly equal to it. It's not an approximation yet. The next step is the approximation. We are setting this up so we can use what's called the binomial approximation. All right. So in this case, I'm going to tell you, does anybody know what a binomial is? Oh, shit. Something's falling down. There we go.
Thing that is 2.
2, right? It's a 2-nomial. Oh my gosh, what is going on here? Oh, this is, oh my gosh. Hold on. Jeez, I'm having some trouble right here. My system's falling apart. Whoa, jeez. Oh my gosh, having trouble. Cords are, oh my gosh. Hold on, I got to untangle my cord now. Ridiculous. All right, binomial. Here's the classic binomial, a plus b to some power n. Maybe you've seen this before. Maybe you know what it is. It's like a to the n plus n times a to the n minus 1 times b plus ... That's a binomial. There's a special type of binomial where the first number is 1 and the second number is small. And by the way, this works with pluses and minus signs too. Well, if we follow the same pattern, if we expand this binomial, if we do the binomial expansion, this is equal to 1 plus or minus n times delta, and then plus n times n minus 1 all over 2 times delta plus ... It's effectively the Taylor series, if you want to think of it that way. But this is called the binomial expansion. I want you to think, if delta is much, much less than 1, what about delta squared? It would be much, 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 much less than 1, right? Because it's much, much less than 1 squared. Look at this. If you do this expansion, this term should be the biggest. This term should be the next biggest. This term already should be getting really small. And even beyond that, the terms get smaller and smaller. So what we say is 1 plus or minus delta to the n is approximately equal to 1 plus n delta if delta is much, much less than 1. This is a useful trick. Think about it. You take something like this, which is severely nonlinear. N could be a fractional power. It could be square roots. It could be negative. It could be positive, whatever. You could take something that's a really nasty function and turn it into a linear function. Isn't that cool? It's going to be approximately valid anytime that's true. How does this relate to what we were just talking about? That's what we've got right here. Delta is a number much, much less than 1. So I'm going to write this again on the other side and hopefully not screw it up. Why is this hanging? Something's going on with my setup here. It's like cables are getting all messed up. Pulling this thing's going to fall over. All right, give me a sec. GMM over R1 plus, okay. Before we found delta U was negative GMM over R times the quantity 1 plus delta final to the negative 1 minus 1 plus delta initial to the negative 1. I know it seems crazy. This is where it gets cool. Hang in there. Okay. Okay. let's use this binomial expansion. Let's use this line of math to simplify these two binomials. And when we do that, we're no longer equals, we're only approximately equals. Okay, what does this first one become? Well, let's follow it through. 1, that's just 1. And let me do red for the first one here. 1 plus n, which is -1, times delta final, minus the other one. 1 plus, oh, I should be careful here. This, if you use a minus sign, you'd get a minus here. I should be careful. Sorry about that. So if you use a plus or minus in here in the math formula, you have to use plus or minus here. But because these both have plus, everything's plus for us. We don't have to worry about that. N is -1 times delta initial. Again, to be clear, this is not equal. It's approximately equal. Approximately. What cancels out?
Put things inside the bracket.
Do they? Look carefully. Some of it does, but not all of it. This is a delta final. That's a delta initial. Are those going to cancel out?
No.
No. What about the ones?
Yes.
The ones drop out. And this is why this problem uses the binomial expansion. People, physicists, love to do binomial expansions when you have two similar terms and you want to do a subtraction, because a lot of times the leading term drops out and only the first order survives. You could ignore all higher order terms, the squareds and all those, and you take a problem that was severely nonlinear and it becomes linear now. These are constants. You just plug those in. It's a constant times some linear function. In fact, well, let's just plug in what it is. Gosh, what is going on today? Must have moved something and I'm losing it. Hold on. Just got to get low here. Check this out. Does anybody remember what delta final was? Well, I'll plug it in here. Let me do this first. There's a minus sign out front. There's a minus sign here and a minus sign here. I'm going to cancel out those. And I get delta U equals G M M over R times delta final minus delta initial. Well, that's equal to G M M over R times height final over the radius minus height initial over the radius. Huh. Let's go one step further. Delta U is thus mass of the block times G capital M over R squared times height final minus height initial. Take a guess what number you get when you begin this stuff right here.
Is it 9.8?
That's G. MGH. Isn't that nuts? They are the same. This MGH that we've been using all semester is valid as long as you're near the planet's surface. But if you go much above 10, 40, 50 kilometers above, you may want to actually account for this other stuff. So at the very beginning of this problem, we were saying, should we use MGH or GMM over R? You could use either one as long as you're close to the planet's surface. But as soon as you're not close to the planet's surface, you've got to use the full GMM over R. That was the point. I don't know if I got that point across, but that's what I tried to do. So questions on that? Isn't that nuts? I think that's interesting. I hope you feel a little bit better about GMM over R and MGH being the same. Whew. Physicists, you're going to need it. So there you go. Now, here's the deal. Why should you care about this? Here's another example. In this is for the speed of sound and air. You could actually rewrite this one as the square root of, I should be careful here, that's kelvins. So I could change this. These are constants. You could say gamma R 273 Kelvin. All over the mass of the air particles, molecular mass, times 1 plus the temperature in Celsius divided by 273 Kelvin, because a degree Kelvin and a degree Celsius are the same size. That works out. More on that in 162, raised to the 1/2. If you do the binomial expansion on this, you get this much easier equation. Doesn't this equation down here in the orange circle that I'm making right now, doesn't this equation down here look a lot simpler for students and professionals than this upper one? I mean, this is a mess, right? Look at that thing. So I don't know how often you're going to use this, but I do know if you're an engineer, you may use the results of it. So having some exposure to what the binomial expansion is will help. This is used for figuring out the electric field associated with a chemical dipole. So this same math is probably used in your chemistry class. Whether they show it to you or just tell you the answer, I don't know. That's enough. All right. If you are a physics major, I threw a couple more problems in here. For example, here's one. You could use the binomial expansion right there to see if you know what you're doing. So, yeah, let me go to the chat. Yeah, I'm sure you're going to see it in chemistry at some point. Just the question is, how much time do they spend on the binomial expansion part of it? All right, but here's another example. Right here. Hint, use a binomial. You'll often hear about the tidal force figured out. And this is actually pretty similar to what we see. We see that in general, forces depend on GMM over R squareds. But when you end up doing the math, you get these weird results that often have cubes. And it's because of the way the binomial expansion works and the math involved, blah, blah, blah. Let's just leave it at that. Moral of the story here. Every once in a while, it comes in handy. Let's stop at that. Questions? Every once in a while, it comes in handy. That's a good enough, right? All right. All right. Let me see what else we got. Chemists and physicists. I know this, I keep mentioning things. If you have ever heard the term reduced mass and wonder what the heck is that and where does it come from, you can look at this problem. Not on the exam, but again, if you might just make a note to yourself. If you're in some class later on and you need reduced mass, you could remember it's somewhere in here. It's got the title reduced mass if you need it. So physicists, we use this as well. So this occurs in the spectrum. So if you've ever done the Bohr model, usually they use the reduced mass of the electron. If you're wondering what the heck is that and why does it work, you can watch this and see how it works out. So chemists, physicists, you better do that one at some point, maybe in the summertime with all your free time. All right. Let's do this here. I think we looked at this problem last time, correct? Pretty sure. Let me pick a different one. Where did I want to go? How about, that's a good one. Let me see. Where's the one? Oh, there it is. Sorry, 13.20. Sorry, it took me so long to get there. 3D. Looks nasty, right? Before we get ahead of ourselves, how do we get the gravitational force of 1 on 5? Somebody walk me through what you think. Try not to look at the solutions. It's going to be ugly. Just describe to me what you would try to do to figure out the force of 1 on 5. Anything you think of. I want the force of 1 on 5. What should we do? I know you're tired, but we only have 2 problems, and then I'm calling class today. So let's tough it out. Help me out here. Let's tell.
Would it be going into the arrow from
Okay. Are you saying the net force should go this way? That would be the net force on 5. Absolutely. But first, I just want to get the force from 4 on 5. So that's the direction of the net force on 5. What's a general technique when we're trying to get forces? What's one of the things you do? Draw. Or what's the equation for force of 1 on 5? Because that may help us draw in this case. Give me a general equation for it.
GM1 times M2 divided by R squared of 1 to 5.
That gets the force magnitude.
Squared, yeah, squared. And then to the negative R hat 1 to 5.
Okay, that's right. So now, what is R1 to 5 hat? The rest of it's probably not too bad, but how do we get that?
What I would do is redraw. I'm looking. No, how far is it? Hold on. I gotta keep going back.
It will help a lot if you tell me how one could compute R1 to 5 hat. That's equal to something mathematically. Does anybody remember how you, generally speaking, get a unit vector? What's the trick that we do? It's a division problem.
It's R hat minus the R magnitude. Wait, correct?
No. The R vector divided by R magnitude. Yes.
There you go.
And so now, what the hell is R1 to 5 vector? Because if we can't get that, we can't get anything. If we can get that, the problem is done. Key thing here is figuring out what the heck this is. What is that?
It's the R1's position. So that's going to be, yeah.
It's that, right?
Correct. I was
Isn't that the same thing as going down to the x-axis, going into the origin, and then going over? Isn't that the same vector?
Yes.
So tell me what it is. Take your time. So I've got to write. So it's going R from 1 to 5. So I think I have the arrows going that way. Take a look at the exponent.
So it's going to be S in the Z hat, S in the X hat, and then Y for the Y hat.
You're on the right track, but look, what's the side of this square?
That's S. Wait,
So
is the whole thing S?
Yeah.
Oh, then it's S over 2 then.
Now look in the X direction. Are you going in the positive or negative x direction?
Technically, you're going, if you're starting from the further from the positive, then you go into the 0, you go into the negative. Correct.
So you just told me it's negative s over 2 I hat.
Correct.
How much in the j hat?
Would you be going down, or would you be going from the point you're going down? So you should be negative then.
No, that's
for
the
j hat. Sorry,
yeah.
y.
So notice
Positive.
we've got to. I have to draw these with the coordinate system you're given. So, is it positive or negative in the j hat?
Positive.
And then in the k hat, I think it's
Net.
negative as well, right?
Yeah, negative s over 2.
Now, we're not going to forget what Alonzo said. That's hugely important. But I want to point out, do you agree we could take all this junk and shove it into here and get it? How would I get R1 to 5? Well, that's just this squared plus that squared plus that squared. X squared plus Y squared plus Z squared. So I should get this. I should be able to get that. What is the net force on 5? Times F1x in the, oh wait, F1 J hat, F1y. Do you agree? Because it's along the y-axis. Again, in this particular coordinate system, y-axis is so depending on whether or not you take the absolute value, the idea is you just get the y component from here, multiply it by 4, you got yourself the net force. And even though this looks like it's going to take all day, the key is correctly writing the r vector, computing this correctly, and then snagging the correct component by symmetry, multiplying by 4. Isn't symmetry awesome? Isn't that cool? Huh. Let me ask you something. Let's say masses 1, 2, 3, and 4 are fixed in place. So let's assume this one, this one, this one, and this one are all fixed in place. But 5 is move. What should it do?
We'll probably want to go back to the origin.
Yeah, and then it'll pick up speed, right? Is it going to stop at the origin?
No, it should go past it.
What is the force on it at the origin?
Would it be
0?
0.
Yeah.
So it's going to be moving. It's going to fly past. How far do you think it would go the other direction?
Until the other force, or until it stops because of the force trying to pull it back.
How far out do you think that would be? Or would it ever stop? Or would it go on to infinity?
Would it just be the same?
It would be the same by conservation of energy. Isn't that crazy? So this is a very weird system where the mass oscillate back and forth. Now, the problem is it's not a simple sine wave, but it would oscillate. If you don't believe me, what could you do to convince yourself that this should oscillate?
I guess you could code it.
Oh, maybe that's what we're doing tomorrow, suckers. So, right, you could test this and see if it works. You could fix these ones and not update them in the loops, right, so that they don't move. And then you could let this one update and see what happens to it. And if it bounces back and forth, that's cool. What if you wanted to get the time to the center of the loop? What's the easiest way to get the time required to the center of that square loop there? Or square, how about, let me say it this way. What would be the easiest way to get the time to the origin? The time it takes to get to the origin. What is the easiest physics trick that we've learned all semester?
Is it kinematics?
Coding it.
No.
That is by far the easiest way. What is the easiest way to get the speed at the center? If I just want
Energy.
the energy problem. If I want the force at the center, forces. And so we see that we're starting to get a range of tools depending on what information is required. You might want to grab a force problem out of your toolkit, or an energy problem, or coding it, or etc. Wolfram Alpha might be useful for doing a calculus problem. All right. One last one, then we'll stop. Look at this one. Give me a sec. This is a really good problem. Take a look at it. There's a question about potential energy. There's a question about force. There's no symmetry. So you kind of have to go through it all, just do the whole problem. And when you look at this one, there's some interesting stuff in these solutions here. Whoa, look at that one. You can calculate the jerk. I did that. There you go. That's interesting. There's that one. $13.21. You could do your energy. That's like we've been doing all day long. Okay. The distances are tricky, so make sure you do it. All right. And then here's different ways of getting the forces. You could do SOHCAHTOA or whatever you want. But so I figured out those forces, and then I added them together and did the gory detail and drew it. I really think if you can handle this problem, you probably can handle the problem on the test for the final exam that involves gravity. Not everybody's going to get the same question, right? Some of you are going to get forces, some of you are going to get energy, but it's basically something either with forces or energy with universal gravitation. That's it. I think you could do that. We're going to code it tomorrow. Hopefully you'll get a little bit more intuition. One warning regarding the coding, you may not, a lot of times people will do it correctly and think they did it incorrectly because things don't move. One of the issues that we're going to have in tomorrow's codes are the numbers are so crazy, right? Our masses are like 1,000,000 kilograms and our radii might be only one. So sometimes you have to play around with the numbers and the simulation speed or the masses before anything will actually move. Because if all the masses are huge and the distances are big, they don't move that rapidly, and you might think it's not actually updating anything. So just, that's the kind of thing I'm going to try and help out with